Hello, aspirant. In this module, we are going to see the analysis of variance, ANOVA in clinical research and bioequivalence applications. Also, we will see the glimpses of two one-sided tests and the data how it is being used in the bioequivalence studies. Analysis of variance or ANOVA is the most powerful statistical tool widely used in clinical trial data analysis. The concept of the analysis of variance is to study the variability in the observed data, partitioning the total sum of squares of the observation into components of the fixed effects and the random errors. Why ANOVA is required? Due to biological and experimental variations, some differences are always exist, and it is necessary to ascertain whether these differences are simply chance occurrences or due to actual differences in the treatment administered to the subjects. Means the errors are just it is happening by chances, or it is due to the actual treatments administered to the subjects in the clinical trial bioequivalence. The statistical methods are used to evaluate the pharmacokinetic data or any other data in order to identify the different sources of variation and, if possible, to measure the contribution of each identified variable and isolate the specific observation of the primary interest. Now we are going to see the types of ANOVA. A one-way ANOVA is a type of statistical test that compares the variance in the group means within a sample while considering only one independent variable or factor. It is a hypothesis-based test, meaning that it aims to evaluate multiple mutually exclusive theories about the data. A one-way ANOVA compares three or more than three categorical groups to establish whether there is a difference between them. Within each group, there should be three or more observations and the means of samples are compared. For example, a professor wants to know if three different studying techniques leads to different exam scores. To test this, he recruits 30 students to participate in the study and randomly assigns each one to use one of the three techniques to prepare for an exam. At the end of 1 month, all the students take the same test. The test scores are presented in these tables. Each group have used each studying technique. And the end of the 1 month, the data has been analyzed by one-way ANOVA and we have got the p-value here. The interpretation of the results is as follows. The F-test statistic is 2.3575 and the corresponding p-value is 0.1138. Since this p-value is not less than 0.05, we do not have sufficient evidence to say that the three studying techniques lead to different mean exam scores. Two-way analysis of variance. A two-way ANOVA is like one-way ANOVA, a hypothesis-based test. However, in the two-way ANOVA, each sample is defined in two ways and resultingly put into two categorical groups. The two-way ANOVA examines the effect of two factors on a dependent variable and also examines whether the two factors affect each other to influence the continuous variable. For example, a botanist wants to know whether or not plant growth is influenced by the sunlight exposure and watering frequency. She plants 40 seeds and lets them grow for 2 months under different conditions for sunlight exposure and watering frequency. After 2 months, she records the height of each plant. After 2 months, the results are shown in the table. The watering frequency is daily and weekly, and sunlight exposure is there is no sunlight, low sunlight, medium sunlight, and high sunlight. And this is the numbers which is indicating the height of the plant grown after 2 months. This is the two-way ANOVA results which is showing the p-value. Now, how will you interpret the results of the two-way ANOVA of the specific example given in this model? The p-value for the interaction between watering frequency and sunlight exposure was 0.31089. This is not statistically significant at alpha level of 0.05. The p-value for watering frequency was 0.975975. This is also not statistically significant at alpha level of 0.05. The p-value for sunlight exposure was 0.000003. This is statistically significant at alpha level of 0.05. These results indicate that Sunlight exposure is the only factor that has a statistically significant effect on the plant height. And because there is no interaction effect, the effect of sunlight exposure is consistent across each level of watering frequency. That is, whether a plant is watered daily or weekly has no impact on how sunlight exposure affects a plant. This table clearly shows the differences between the one-way analysis of variance and two-way analysis of variance. By definition, one-way ANOVA allows one to make comparisons between the means of three or more groups of data. On the other hand, two-way ANOVA tests allows one to make comparisons between the means of three or more groups of data where two independent variables are considered. The number of independent variables in one-way ANOVA is 1 and two-way ANOVA is 2. And we compare the means of three or more groups of the independent variable on a dependent variable in one-way ANOVA, where in two-way ANOVA, the effect of multiple groups of two independent variables on a dependent variable on each other will be compared. The number of groups of samples will be 3 or more in one-way ANOVA, and in case of two-way ANOVA, each variable should have multiple samples. Now, we're going to see the ANOVA, specifically how it is connected to the bioequivalence and the sources of variation in bioequivalence. The pharmacokinetic parameters derived from blood drug concentration and time data in the bioequivalence studies are subjected to ANOVA analysis. ANOVA will be performed on the pharmacokinetic parameters like AUC and Cmax, accounting for the sources of variations which are sequence, that is the group, subjects in the sequence, then the period, then the treatment, that is the drug formulation test error. And the results of the ANOVA are calculated at the level of 5% significance. In a bioequivalence study, once the ANOVA analysis is done, this ANOVA table is how it is being presented is given in this particular slide. In this table, there are different sources of variance is listed and the degrees of freedom, sum of squares, mean sum of squares and F statistics is given. Here, T is the number of treatments, SST is the sum of squares due to treatments, SSP is the sum of squares due to period, MSS mean sum of squares due to subjects, MST is the mean sum of squares due to the treatments, MSP is the mean sum of squares due to the period, and finally N is the number of subjects. This is how in a bioequivalence study the ANOVA table is present. This slide shows the ANOVA table for parallel group design with two treatment with n number of subjects. In ANOVA, the mean sum of squares is compared with the mean sum of squares due to error. That is F is equal to MST divided by MSE. And if these are comparable, no difference between the levels of a factor is concluded. Otherwise, a difference is achieved. F is equal to between group variance divided by within group variance. The treatment mean sum of squares is larger than the error mean sum of squares if difference is achieved between the treatments. Then the chances of getting treatment mean sum of squares being bigger than the error mean sum of squares are more in crossover design compared to the parallel design. Therefore, chances of showing that a statistically significant difference are higher in crossover design compared to the parallel design. If the trial is run under tightly controlled conditions and the number of subjects is large enough, no matter how small the difference between the formulations, and it will be detected as significant. The difference may give rise to anomalies or abnormal values due to a large difference between two formulations, then the sample size is not large enough. That means the difference may be increasing due to the abnormal values found in the treatments. Then it will affect the sample size and the sample size may not be enough to detect the difference. What is sum of squares treatment and sum of squares error? In ANOVA, the between and within group variability is presented as sum of squares in the ANOVA table. Sum of squares for treatment is nothing but between group sum of squares, and the sum of squares error is the within group sum of squares. Total sum of squares, that is TSS, is equal to SST plus SSE. Now we have seen some introduction to the ANOVA analysis and how it is being used. What is sum of squares in treatment, sum of square in the errors. Now we are going to see the two one-sided test procedure. This is widely used in the 90% confidence interval calculation, the bioequivalence conclusion or some other experimental procedures. The most common way of performing equivalence test uses a procedure called two one-sided test. There will be a two separate hypothesis tests are performed using test 1 and test 2. In test 1, H0 is presented like this and HA presented like this. In test 2 scenario, it will be presented with the value of 1.25, where in the test 1 it is presented with the value of 0.8. If both null hypotheses are rejected at the alpha percentage significant level, then equivalence between the means will have been demonstrated at the significance. According to the US FDA, the difference is set at -20 or plus 25%. In order to verify that -20 or plus 25% rule is satisfied, the two one-sided tests are carried out. The rejection of two one-sided tests null hypothesis at 5% level of significance is equivalent to the inclusion of the 90% CA in the acceptance range. Now, we will try to understand why logarithmic transformation of the data is required in the bioequivalence study. Bioequivalence studies measured and compare statistically AUC and Cmax of the formulation. In case of AUC and Cmax, the regulatory authorities recommend that they should be logarithmically transformed before further statistical analysis. The use of log transformed values of AUC and Cmax is recommended for several reasons. The reasons include clinical reasons, pharmacokinetic reasons, and statistical reasons. What is clinical reasons? The primary comparison of interest in the bioequivalence study was the ratio rather than the difference between average parameter data from the test and reference formula. This is achieved statistically by using log transformation. Then what is the statistical rationale or statistical reasons? Many biological data correspond more closely to a log normal distribution. AUC and Cmax tend to be skewed and their variances increase with the means. Log transformation makes the variances independent of the mean and the frequency distribution is made more symmetrical. Now, why logarithmic transformation is required and the pharmacokinetic reasons for the same. The most biological variables PK metrics, that is AUC and Cmax, follow log normal distribution. If they would follow a normal distribution, that is the bell curve, the range of possible values by definition would be minus delta or plus delta. However, negative concentrations are not possible. The log normal distribution covers the range of more than 0 or plus delta. In statistical methods we apply in bioequivalence, we need normal distribution data. If we log transform the original data, we get exactly what we need, and at the end of the analysis, we back transform the result. That is the 90% confidence interval of minus delta value, that is 0.1832 and plus 0.0432. Then once we back transform that, we get the value of 83.26% and 104.41%. The 90% confidence interval is calculated by using this formula, and it indicates the least square means from the ANOVA and the t-test statistic with the 0.051 time and the standard error observed in the data. Finally, the BE criteria is 90% CA of the ratio of log transfer PK data should be within the range of 80 to 125. So with this, we are concluding the module which talks about the ANOVA and two one-sided tests and why the study data in the bioequivalence studies is transformed into the logarithmic data. Thank you.